Hi, everybody. Welcome back to the Feynman Technique. I know I haven't posted in a while. I've just been a little busy. I've been working on a paper for publication, and the paper is a unique proof of the Basel problem value, basically the sum of the reciprocals of the squares. I've been working on that. I should have it published hopefully by the end of the year, but I'm pretty excited about it. It would be my first actual published paper. But anyway, that's what I've been working on. I've been refining it, making it a little bit more rigorous. But anyway, today I have this integral right here, and we're going to solve it with Feynman integration, and it's fairly basic. This is classic Feynman integration, so let's just get into it. All right, so the first thing we're going to do is we're just going to define a function of t that is very similar to our original integral. And this is what we're going to do. We're just going to put a t right in there. Now let's notice a couple things about this. If we evaluate f at the point 1, we recover our original integral. So f at 1 is equal to I. And also, if we take the limit as t goes to infinity of f of t, right, f of t, we get 0. If we plug in infinity, if we let t approach infinity, this term right here goes to 0, making this entire integral go to 0. All right. So next what we're going to do is we're going to differentiate under the integral sign. Now, we can use the Leibniz rule for differentiation under the integral sign to take the derivative of our f of t just by bringing the derivative directly inside the integral sign with differentiation under the integral sign. Okay, so we need to take the partial derivative with respect to t of this. And I'm not going to show the work here. All that's what that's going to give us is negative integral 0 to infinity of 1 minus cosine x times e to the negative tx dx. And let's just verify that that's true. All right, so that's, let me bring this over so we can see what the graphs look like. As you can see, this green one is our derivative, and this is our original function. So I'm just going to put a d dt in front of that to make sure that it matches. So we should get overlapping graphs once this finishes calculating. And as you can see, it does. They overlap. They're the exact same function. Okay. Let's put our notation back. Desmos does not like prime notation, so I usually have to just put a subscript 1 to indicate the derivative there. But anyway, so now we have f prime of t is equal to this. And I'm not going to go through the steps of solving that integral. Let me get rid of the graph there. But what we end up with is f prime of t is equal to negative 1 over t times t squared plus 1. You can pause the video and verify that for yourself if you'd like. But that is what we end up getting. Okay, so now we have f prime of t, but we don't want f prime of t, we want f of t. So we have to integrate back. So f of t is just going to be the antiderivative with respect to t of f prime of t. In other words, it's going to be negative indefinite integral of 1 over t times t squared plus 1 dt. Again, I'm not going to, this is a standard integral. We can evaluate that fairly easily. So I'm just going to skip right to the answer. And what we would get if we actually evaluated that was this. So, of course, we would have plus c. Okay. So now we need to take care of that constant of integration. Sorry about the dog whining in the background. So let's use this. The limit as t goes to infinity of f of t is equal to 0. Well, that's going to be equal to the limit as t goes to infinity of our f of t. Okay. So, what is the limit as t goes to infinity of this? It's pretty clear that the limit is going to be this part is going to be 0. So we have 0 is equal to 0 plus c. That implies that c is equal to 0. So our final expression for f of t is just this part right here. All right. Now, let's go back up here where we stated that f of 1 is equal to our original target integral. So we have f of 1 is equal to I. Well, that's equal to this, where t is equal to 1. So this is going to become a natural log 2. This will become a natural log 1, which is 0. And we just end up with natural log 2 over 2. And let's just go ahead and verify that that is correct. Let's go back up here to our original integral. Natural log 2 over 2. Yeah, so they match. And that's it. All right, guys, hope you enjoyed that, and we'll see you next time.